the previous lectures, we covered about the Maxwell-Boltzmann distribution law. The condition is that the particles are all distinguishable and there is no restriction to the number of particles at any energy level. Then we discussed about the Bose-Einstein statistics, which says that the particles are indistinguishable and there is no restriction of the number of particles at any energy level. Now we will look into what is known as the Fermi-Dirac statistics. Particles which obey these statistics are called fermions. I told that particles which obey Bose-Einstein are called bosons, and the particles which obey the Fermi-Dirac statistics are called fermions. Now the condition is again, in Fermi-Dirac statistics, the particles are indistinguishable, similar to Bose-Einstein, but there is a restriction to the number of particles at any energy level. Something like, we say that an orbital can accommodate only 2 electrons. We say that no 2 electrons can have all the 4 quantum numbers the same. So there is restriction in the Fermi-Dirac statistics. And the formula for maximum possible distribution is W equal to Gi factorial by Ni factorial Gi minus Ni factorial. This is the formula for maximum possible distribution. Now let us assume we have two cells X and Y. I want to distribute 4 particles into these 2 cells. In cell X, the degeneracy is 4. I want to distribute 3 particles in this, but the condition is each energy level can accommodate only 1 particle. That's the restriction I said. So in the 3 particles, they will have, I'll distribute like this. This is one possibility. This is another possibility. This is another possibility. This is another possibility. So only 4 possibilities are there. Let me apply the formula and calculate. I said the formula is W equal to Gi factorial by Ni factorial Gi minus Ni factorial. The degenerate energy levels are 4. So it is 4 factorial. Number of particles to be distributed is 3. So Ni equal to 3 factorial. And Gi minus Ni factorial is 4 minus 3 factorial. That is equal to 4 into 3 into 2 divided by 3 into 2 into 1. So there are 4 possible distributions according to Fermi-Dirac statistics. That's what I have shown here. Now let us say I have a cell Y. Where I am going to distribute only 1 particle. Only 1 particle, namely one here, or it may be here, or it may be here, or it may be here. No other possibilities are there. Again, by applying the formula W equal to Gi factorial by Ni factorial Gi minus Ni factorial. Degeneracy is 4, So it is 4 factorial in the numerator. Ni, I am going to distribute only one particle, and Gi minus Ni, 4 minus 1 factorial. That is equal to 4 factorial by 3 factorial. Again, the answer is 4. So total ways of distribution are pi W equal to pi Gi factorial divided by Ni factorial Gi minus Ni factorial. So it is 4 possible ways in cell X, 4 possible ways in cell Y, totally 16 possible ways are there. Very simple to understand that. So this is one way of distribution, this is another way of distribution, this is another way of distribution, and this is another way of distribution. So for this you have 4 possible distributions. Similarly for this, so on and so forth. So 16 possible ways of distribution are there. This is the Fermi-Dirac formula for maximum possible distribution. So I will write the formula as W equal to pi Gi factorial by Ni factorial Gi minus Ni factorial. This is the formula. So let me take logarithm for this. Ln W equal to, so the product will become summation Ln Gi factorial minus Ln Ni factorial plus Ln Gi minus Ni factorial. I am going to apply the Stirling's approximation. I recall what Stirling's approximation is. For a factorial of a large number, the Stirling's approximation says that n factorial equal to n ln n minus n. This is applicable when n is a large number. So these numbers are all large, so I am going to apply Stirling's approximation to this, and what I get is, it is equal to sigma Gi ln Gi minus Gi minus Ni ln Ni minus Ni plus Gi minus Ni ln Gi minus Ni minus Gi minus Ni. I just applied Stirling's approximation to this. That is equal to sigma Gi ln Gi minus Gi, I am removing the brackets now, minus Ni ln Ni plus Ni plus let me write like this, later we will remove the bracket, why to confuse. Minus Ni ln Ni plus Ni minus Gi minus Ni ln Gi minus Ni, minus of minus is plus Gi minus Ni. This is the expression for ln W. I think plus Ni and minus Ni cancels off. minus Gi and plus Gi cancels off. So the expression becomes L and W equal to sigma Gi Ln Gi minus Ni Ln Ni minus Gi minus Ni Ln Gi minus Ni. Okay. W is the maximum possible distribution. So W is maximum. Therefore, L and W is also maximum. Hence, I can say dL and W is equal to 0. Since it has reached maximum, there will not be any further change. So let me differentiate this and put it equal to 0. So d Ln W equal to sigma differential of this Ga is a constant. So differential of this will be 0. So only this will be differentiated, undergo differentiation. So dL and W equal to sigma ln of Gi minus Ni by Ni dNi. Since W and L and W are maximum, the differential of this is 0. So this is equal to 0. This is the condition for maximum possible distribution of fermions. In addition, we will say sigma dNi equal to 0. The meaning of this is the change in number of molecules at any energy level. If you add up the change, that will be equal to 0. That is, if 3 particles decrease in one energy level, 3 particles will increase in another energy level. So the net change is 0. This is the second condition. And the third condition is total energy is also constant. Total number of particles is constant. Total energy is also constant. So I will say Ei dNi is equal to 0. These are the 3 conditions for maximum possible distribution of fermions. Let me multiply this by alpha, multiply this by beta, and from them let me subtract this. So what I get is sigma alpha dNi plus beta Ei dNi minus Ln Gi minus Ni by Ni dNi is equal to 0. This is the condition for the maximum possible distribution of fermions. Or I can write it as alpha plus beta Ei minus Ln Gi minus Ni by Ni dNi is equal to 0. dNi is not equal to 0 because molecules can move from one energy level to another energy level. So dNi can't be equal to 0. So this must be equal to 0. Alpha plus beta Ei minus Ln Gi Ni by Ni equal to 0 is the condition for maximum possible distribution of fermions. Or I can write it as or I can write it as alpha plus beta EA is equal to ln GI minus Ni by Ni. Okay. Removing logarithms, I can write it as e power alpha, e power beta EA is equal to GI minus Ni by Ni. Or I can write it as e power alpha, e power beta EA is equal to GI by Ni minus 1. Let me take this minus 1 to the other side. E power alpha, e power beta EA plus 1 is equal to GI by Ni. We need the expression for number of particles at any energy level Ni. So rearranging, I can write Ni equal to GI by e power alpha, e power beta EA plus 1. This is the Fermi-Dirac distribution law applicable to particles which are indistinguishable. At the same time, there is restriction to number of particles at any energy level. We have discussed all the three statistical procedures to calculate the number of particles at any energy level. Maxwell-Boltzmann, it's called the classical distribution law. Bose-Einstein, applicable to particles which are indistinguishable and there is no restriction for the particles at any energy level. And Fermi-Dirac statistics, applicable to particles which are indistinguishable but there is restriction to number of particles at any energy level. Now, using these statistical principles, in the introduction itself I told you, you can calculate a number of thermodynamic parameters. So the application of these statistical procedures is to calculate the thermodynamic properties like entropy, free energy, pressure, all these things could be calculated. Let us look into this aspect now. So I am going to talk about application of partition function in calculation of thermodynamic parameters. I am going to apply the classical distribution law for this calculation. Okay, now I want to calculate the total energy of a system. The total energy U is equal to sigma Ni into EA. Ni, according to the classical distribution law, is equal to N by F into e power minus EA by KT. So let me substitute that here, and what I get is U equal to sigma EI into N by F e power minus EI by KT. I can write it as U, the internal energy, is equal to N by F into sigma EI into e power EI by KT. We know by definition the partition function F equal to sigma e power minus EI by KT. Let me differentiate this. dF by dt equal to sigma EI 1 by KT square e power minus EI by KT. Or I can say KT square into dF by dt equal to sigma EI e power minus EI by KT. I am going to substitute this in this expression. If I do so, this is equal to N by F. This quantity is equal to KT square dF by dt into KT square dF by dt. Or I can write it as NKT square dln F by dt. dF by F, I have written it as dln F, where N is the number of particles. If it is 1 mole, I will write it as, I will replace this by Avogadro number. N or L, you can use it. Both of them are used for Avogadro number. Capital N or L can be used. So this is the expression for the total energy of a system. Okay, so I have an expression now for the total energy is equal to N KT square dln F by dt. If it is for only one molecule, N equal to 1, I will write it as U equal to KT square dln F by dt. So the internal energy of a system can be calculated from a knowledge of the partition function. Then entropy can be calculated. Entropy, S can be calculated. Already seen this definition, S equal to Nk ln F plus K beta U. We have seen that beta equal to 1 by KT. So this simplifies to Nk ln F plus K 1 by KT into U. So Nk ln F plus U by T is the formula to calculate S. You know what is U. So let me substitute that value for U. So U equal to NKT square dln F by dt is U. Or simplifying this, so this simplifies to Nk ln F plus NKT dln F by dt. So this is the expression for, so entropy can be calculated from a knowledge of the partition function F. So let me write it here. S equal to Nk ln F plus Nkt dln F by dt. By just substituting these values, it is possible to calculate what is the entropy value. The third thermodynamic property which we can calculate is the work function A. Definition for A, you know that, is equal to U minus Ts. Definition for G is H minus Ts, and definition for A is U minus Ts. I know the value of S, I know the value of U. Let me substitute here and see what I get. So A equal to, for U I will substitute N K T square dln F by dt minus T into, for S I am going to substitute this, N K ln F plus N K T dln F by dt, or A equal to nkt square dln F by dt minus nkt ln F, minus into minus plus nkt square dln F by dt. There is a minus here, therefore this becomes minus. So these two cancels off. Therefore A equal to minus N K T ln F. So if you know the value of partition function, you can calculate A. A equal to minus nkt ln F. Then pressure also can be calculated. Pressure P can be calculated. The procedure involved is this. A equal to U minus Ts, dA equal to du minus Tds minus sdt, by the definition for ds equal to q by t. So I can write it as dA equal to du minus t into q by t minus sdt. So dA equal to du minus q minus sdt. Q is nothing but, according to first law, Q is nothing but du plus pdv. This is the definition for Q according to the first law. So let me substitute that here. So it is equal to du minus du plus pdv minus sdt, or it will be simply equal to, these two will cancel off, minus pdv minus sdt. Let me differentiate this with respect to volume at constant temperature. That is dA by dV at constant temperature equal to minus P. I know what is A. So let me substitute that and differentiate with respect to volume. So what I get is, since at constant temperature, SdT has become 0. So it is dA equal to dA by dou A by dou V at constant temperature is equal to simply minus P. I know A equal to minus NKT ln F. So dou A by dou V at constant T equal to minus N K T dou ln F by dou V at constant T. So minus P is equal to this quantity. So let me write it then as minus P equal to minus NKT dou ln F by dou V at constant temperature. So pressure equal to NKT dou ln F by dou Vt. This is the expression for pressure. So P equal to N K T dou ln F by dou V at constant temperature. So the pressure can be calculated. The Gibbs free energy G can also be calculated. Okay. G equal to A plus PV. A is nothing but U minus Ts, and G is nothing but H minus Ts, H equal to U plus PV, therefore I say U minus Ts is nothing but A, so this is A plus PV. Okay, so we know the values of A, P, we can substitute here. So G equal to A is minus NKT ln F plus P is NKT dou ln F by dou V into T into V. Or I can write it as minus NKT ln F plus NKT. If I bring this V here, dou V by V will be dou ln V. So dou ln F by dou ln V. So G equal to, if I take NKT as common, it is ln F minus dou ln F by dou ln V at constant temperature. So I can write G equal to minus NKT ln F minus dou ln F by dou ln V. H can also be calculated. It is very simple to calculate. H equal to U plus PV. We have expression for U We have expression for P, just substitute, nothing else. So H equal to nkt square dln f by dt plus, for pressure I am going to substitute this, nkt dou ln f by dou vt into V. I can bring this V here and I can write it as dou ln V. So H equal to nkt square dln f by dt plus nkt dou ln f by dou ln V at constant temperature, or H equal to nkt dou ln f by dou ln t. I just taken one t here, dt by t is d ln t, plus nkt dou ln f by dou ln v, or nk into nkt I can take it as common, dou ln f by dou ln t plus dou ln f by dou ln v. This is equal to H. That's about H. So any other parameter can be calculated. Say for example, you can try it. I know the definition for the molar heat capacity at constant volume. The definition is nothing but dou U by dou T at constant volume. You know the expression for U. Differentiate it with respect to temperature and substitute. Take it as an exercise, do it. So all the thermodynamic parameters can be calculated from a knowledge of partition functions.